Hello, I'd like to continue talking about the network layer. The first thing I want to talk about are routers, or whatever you want to call it, however you want to pronounce them. A router connects two or more sub-networks. It has the following parts. It has software to compute routes on the internet. Routes are computed, they're stored in a table in the router's memory. Now we'll look at that in a few minutes and the algorithms that are used. It has a set of input lines, a set of output lines. There's one line for each neighbor that we can send to and one line for each neighbor that we can receive from. The funniest part of it, or the part that seems to have a strange name, is the fabric of the router. This is the way messages are moved from the input line to the output line. There are three possibilities here. The message might come in and it is stored, and the output lines have the logic, they have the program to read the headings and pick the messages they are supposed to send. Another way would be all the lines are connected on a bus. Remember, a bus is just a communications device, a line between different devices. And the output line can see what messages it should take from the bus. So the input line puts the message on the bus, and the header contains the information for what the next hop in the route is. Third one is each input line has a bus, and each output line has a bus, and all the input buses connect to all the output buses. Now, first, I want to show you this. This is a picture from the internet of one of the Cisco routers. There are input lines on one side, output lines on the other, and the switch fabric, the lines that come in for each of these. You have the buses that take the input, the buses that take the output, and they're all connected to one another. So it's kind of quite a mess, as you can see. There's a very good place on the internet that I want you to look at. I have it here. It's what's inside a router. You can see it has what I was talking about, the input and output ports, the switching fabric between them, and the routing processor, which executes the routing protocols. And that's coming. And you can see here, there's various pictures of it. There's the bus, the crossbar, and the just straight through lines that I was talking about, where the output line figures out which ones are for it. And there's more here, shows the idea of queuing. And I think this would be interesting to look over for you. I don't feel like reinventing the wheel. It's already there, so why not just use it? Now, back to where I was, right here. One thing to think about is, what does the router table look like? And I think I'm going to fix it so this starts on a new page. Now, if you look at this, we have ranges in the router table. So anything that comes in from 162.93.84.16 to the same three things, 0.31, it goes out on line 1. Excellent. And if you look, we can rewrite the 24 bits, first 24 bits are the same, they're the same digits. 16 is 1000, 31 is all ones there. So the next three bits are also the same. So we could write this. In fact, the first 4 bits are the same, pardon me. So we can take these 24 and these 4, and we could write this in CIDR notation as 162.93.84.16/28. And that means we can change the last 4 bits, nothing else. Now, if you look, this is actually part of that. But it's going out in a different line. So what are we going to do here when something comes in? If it comes in from here, if it's going to this destination, does it use this route or does it use this route? It fits into both of them. The usual rule is called the longest prefix first. It starts at the bottom of the table. Now, if you look at these, if something comes in that area, then it's more specific than what's up here. This has 24 bits set, 28. This has 30 bits set. So since this has a longer prefix, we choose that and not the one that it's a subgroup of. Now, so far we've talked about the addressing functions in the network layer. Now it's time to talk about the routing. This is the first time when we have talked about the entire route from the source to the destination. Up to now at the transport layer, all we've done is identify the destination we want. We're at a source, and we let the lower parts of the network figure out how to go from one to the other. The same thing at the application layer. We didn't worry about how we're going to get across the network. Well, it's time somebody's got to do it. So it's the network layer that does it. The question is, what's the best route? Now, we might colloquially call that the shortest route. Well, is that the one with the fewest nodes? Or is it the one that can get us there the fastest? Or is it the one that will cost us the least money? Or more likely our ISP, Internet Service Provider, the least money? Those are all possible definitions of shortest. However, it looks pretty likely that we are going to be assigning some kind of cost from one node on the network to another, say from one router to another router, directly connected. It makes sense there's got to be some cost. If the network were perfectly homogeneous across everything, we could put one there, and our cost could be the number of hops we take, how many routers we go through to get from source to destination. But usually that's not true. And things can change. A network can become very congested in one part. And so instead, the router can recompute routes and say, I better take this alternate route. It's faster right now. I used to think this route up here was faster, but it's not there. It's not as fast. In fact, even worse things can happen. The route I have can have a node on it that dies. It's not there anymore. Now what? Well, I got to have an alternate route. That's why there are always more than one route to get from one place to another. Now, There are two ways we can think about roots. The first way we can think about roots is that a node knows everything, at least in its little group. We're not talking about creating a root through all billion or whatever there are of nodes. What we're saying is our system, our little part. So our subnetwork. That's the interior gateway protocols we're going to use. Then the nodes that are connected on the backbone of the internet, they create their own roots from one of them to another one of them. So it's a hierarchy. My computer probably knows how to get to my gateway to the internet. That gateway looks at where I want to go, and it knows what next gateway it should send my message through. And when I use gateway, I'm meaning a router. So there's two parts to it at least. There is the internal part that is my part of the network, and there's the connections that connect all those little internal parts. Well, within each of those, there's two possibilities. First of all, every node could know everything about its system, about the place it's trying to produce the root. So it could have all the information. Now, to get that information, there was probably a massive exchange. Each node told its neighbors what it knew. And gradually that built up so that each node knew everything about that area. Now, if you think back, I suspect most of you have seen at some point an algorithm called Dijkstra's shortest path algorithm. This is one of the most famous algorithms in computer science. And basically what it is an algorithm that says, I know everything about the network. I'm at node A. My job is to find the shortest path to each of the other nodes. Now, they're global because they can be done by any node in the group. What that means is that each node figures out its own best ways. So it's not as if one node has to compute everything. All the nodes compute their best paths. Now that's one possibility, but that possibility has a drawback. You have to get that information, and it can change. So you have to use some of the bandwidth to send out what you know about your neighbors to your other neighbors. A second approach says, all I know is how I can get to my neighbor. Those are the only things I know. I know who my neighbor is and how I can get there, how much it costs me. Now, these are the Bellman-Ford algorithms. Ford is not any related to me. I don't even know who that Ford is. These are local algorithms, mainly because each node only knows a little bit. The backbone computations in the internet usually use that method. The interior ones for the small autonomous systems usually use Dijkstra. Now, let's see. What I've got here is an example of Dijkstra working, which I think I might postpone going through all the details, but you can begin looking at them. Dijkstra is not very difficult. All you do in Dijkstra is, I'm looking at the, let's see, I'm working at location B, node B up here. and I want to know how to get to any other node from B. So when I begin, I know that B is connected to A, to C, to D, and to H. So I have the distance to A, to C, to D, and to H. As far as I'm concerned, I don't know anything about the other distances. They know one another, but I don't. Now, I look here and say, what's the shortest path I have so far? 2, to get to A. Well, that can't be improved. All my other B paths have to come off these. So that's it. That's the best path to A. So now I put over here that B and A I know how to get to for the shortest path. Next step, I look at all the paths that I have left here. Now, does A tell me anything I don't know already? I guess that's what I'm asking. Well, B has told me that it knows how to get to H and C and D. But H told B how to get to E. And D also told B how to get to E. So I know more information. And G told me how to get to F. So now I computed that if I want to get to G, I can go, B says, I can go from A to G. Because I'm sorry, I thought I was at A for a minute. I'm at B. A tells me, hey, I can get to G in 1 unit. Well, B says, oh, I can get to U in 2, so that means I can get to G in 3. And B was told by H, I can get to E in 3 units. Well, it takes me 9 to get there, so that's 12. That's pretty major. C says I can get to D in 10. That's going to cost me 22. I had 23. 22's better. I'll take the 22. And I just keep building up this way. Now I know more. I know how to get to G and I know how to get to E. So I look and see what's the best path I have? Well, the one to G. So I set that one to fixed. And now I repeat what I was doing. I get more information. Actually, what I'm doing is I'm expanding the best nodes, the ones I really know, or the ones I don't know any. I know AGF now. I know AGE now. Well, that looks pretty good. I'll take one of them. HGE, that's better than the AG7 and AGE. I'm beginning to wonder why I took AG7. Oh, this should have been bolded. That's the problem. That one I took there. Okay. In case you're wondering why I'm looking down, I finally have a cat that's come out to be petted. And boy, does she want petting. So I'm doing that while I'm doing this. And you can just see I keep going till I finish them all. And I have the paths when I finish, because I've been building them up one by one. Well, that's the Dijkstra algorithm. It really isn't, come on up here, girl. It isn't really that hard. It's a reasonable algorithm. The books have details for it, but I think it's easy to just think it out. The other algorithm is more complicated. And believe me, it can be more complicated. Now, in this algorithm, node A says, I know that the cost to B is 2, and I know the cost to G is 1. So B starts out, and everybody exchanges information. So A hears from B. B says, I can get to C and H, and puts in what it takes to get there. And then it says, I've got D and H. And G tells me it can get to H. So now I've got more information. Oh, pardon me, that was at node B. At node G, I have this. Everybody exchanges information. And I now build up my table at B. Unfortunately, that happens everywhere, which makes this a very difficult algorithm to do simply. You have to keep things everywhere. I have an example in more detail that I will do later. Right now, I just want you to take a look at these, and you know, and I know, that you're going to get a homework on these very soon. That's not a threat. It's just telling you, be alert, it's coming. So that's where I am right now. I hope you had a good mental health